The following program is brought to you by Caltech.
Okay, the next speaker is going to talk about capturing flight software with a domain-specific language. Kim Gostelow's expertise is in the design of real-time software systems and the use of languages to program them. Kim has been at JPL for over 20 years. During this time, he has developed attitude control flight software for Mars Pathfinder and Cassini. He was the principal flight software lead for the MER and MSL missions for the GNC software. Prior to joining JPL, he was professor of computer science at UC Irvine. Currently, Kim is a PI on several R&D projects. These include a multi-core demonstration for fail operation flight computing, knowledge of computer control and a spacecraft state R&D project, and he is the software architect for the Landing Vision Test Bed, which is a terrain relative navigation test bed at JPL. Kim holds a PhD in computer science from UCLA. Kim.
Okay, so I wanted to talk about the utility of a domain-specific language. And Bob talked a little bit about the importance of layered design so that the conceptual understanding of the system at that particular layer has an architecture of its own. And if the architecture is correct, it should be easy to write programs in that particular layer. So the domain-specific language I'm going to be talking about today, which is under development, is really at a pretty low level. It would be at a level below that of the kinds of systems that you would call a resilient system. People building resilient systems might use this layer as their programming language. So I said it was very low level, and since it's software, we're going to talk about hardware first. Most everything that we can do with software, at least those who are interested in the practical applications of software, are really limited or empowered by the particular hardware that's available. So we all know that microcircuits are have reached a limit as far as speed is concerned. So they've been branching out and using more processors. Everybody's laptop probably has at least a couple of cores in it. The particular chip that I have up here is one from Telemetry Corporation, which we actually have a couple of these at JPL that we've been working with. And it has 64 cores. They are in development of making 100-core chips as well. And each tile, I guess there's a pointer someplace. Is there a pointer? Oh, is it this thing? There we go. So each one of these tiles looks like this. There's a lot of communication with nearest neighbor. There is an engine that keeps track of messages as they flow through. There is a thing for running the memory system. And of course, there's a processor. Now, when they put all this together in this particular machine, there wasn't room for floating point. So that is definitely a shortcoming because, of course, we do a fair amount of floating point calculations in GNC software, and that causes things to slow down. So there was a follow-on project, which is called Maestro, that is a rad-hard implementation of this chip, but they had to sacrifice a row and a column. So that has 49 cores in it, but each core has a floating point system. So what I'm trying to get at by talking about this particular chip is that these things are coming. And one of these days, we will be flying multi-core chips of this nature on spacecraft. And in fact, what we really are looking forward to is when we will have thousands of cores, thousands of processors on the spacecraft, with the cores distributed, high-speed interconnect, And when you imagine a system like that, this is really what I think people think about as a knob that you can simply turn the power up and down, and you can turn a knob, say, for speed and a knob for reliability. There's a trade-off amongst those things, but these are adjustable. So during some phases of the mission, you may want to run with low power, because power remains still a critical resource on spacecraft. And you have to decide, or the system has to decide, whether speed or reliability is what's important. And conversely, if we come to a phase in the mission that's important, an event is coming up, say it's EDL, then it's probably a good idea to up the reliability, and you pay for that by adding some power to the system, and you're willing to pay for that in order to get the increased reliability. So that means that computations will need to reorganize in real time, that there's a degree of introspection involved, that the system has to decide just which programs it's going to make more reliable, and I'll talk about what that means. And we really want to make things so that there's really little or no consideration needed by the programmer. We spend a lot of time and a lot of money now writing software where we have to work with very low-level things, bits and bytes, and over again, they cause errors. They all have to be tested, and it's just very expensive to build flight software. So what we want to do is to raise the level at which people write programs, and that's kind of the theme of what this talk is about, and that is a domain-specific language where we can capture the ideas that we have, the things we know how to do, and build them into the language with the expectation that the programmers can put systems together more easily, more cheaply than we currently do. So we do a little bit of parallelism. We have concurrent tasks that are running. But as I mentioned, we do spend a lot of time putting all that together. And of course, a lot of work is done on supercomputers where there's massive amounts of processors running. But a lot of those are written in such a fashion that they're very intricate and very carefully laid out and orchestrated. And that's not the kind of thing, I think, that we need to depend upon, or we're going to lose our reliability, our ability to turn power off and to move things around and to reorganize the software while the system is still running. And we want that reorganization to take place without the programmer having to do anything. It's system code that was written once that takes programs, turns them off, turns them back on again, restarts them, reruns them, and moves them to different places in the machine according to what's available and where the power is. So one idea that's been around for a long time, actually, is that of functional programming. And I'll get into a little bit of detail about it and give some examples. But the basic issue goes back to the idea that we run with von Neumann computers and von Neumann programming languages. So what that means in particular is that if you write a program, say in C, and you have a variable, an integer called x, that variable is not really a mathematical variable. It's really a memory cell. And an example of why that's a memory cell and not a mathematical variable is you can write statements in C of the form x equals x plus 1. Now, mathematically, in the domain of integers, that doesn't make a lot of sense. But in computers, it makes perfect sense, at least in this kind of a computer. An instruction executes when the program counter reaches it. That's not a concept in mathematics. So the idea of functional programming is to go away from these kinds of behaviors and to write programs that are functions. What that's going to mean, and I'll show some examples, is that when you compute the value of x, it will never change. Once it's defined, that's its value. And secondly, really no shared memory. Shared memory is an issue because it defeats this definition of a function. So it's kind of a mimic of the mathematical definition. It says that you have a function that takes you from argument to result, and it says that for every argument, there is a unique result. So in other words, every time you run function f, both mathematically and on a computer, functional programming means you will get the same answer every time. Now, you think about some example programs that you write, that's not necessarily the case. For example, if we look here, program A, I'm going to show that this is not a function. Internally, and in fact, there's several reasons why in this particular program. One of which is that this, if it's a function, it depends upon all of its insides have to be functions also. But get time of day is not a function. It produces a value that depends upon what time it is. So every time you call it, you generally expect a different answer. Another reason that this is not a function is that you'll notice the variable sum here happens to be globally available. What is to prevent somebody else in another thread, in some other part of the machine, changing the value of sum while you happen to be running? And in particular, two threads could be running the same function, and they can interfere with one another. So this is not a function because it uses shared memory. And finally, it's not a function because here we have defined the value of sum here, but every time we iterate through this loop, we're redefining what sum is. It has a different mathematical meaning. So over here, I've kind of rewritten this in a functional way. Here, what we're doing is that we're computing a vector, v, to hold the result of f for each I. So once v of I, v of 0, 1, 2, 3, and so forth, is defined, it's not changed in this program. There's no shared memory. And the result that's computed that depends upon time is now an argument to that function. So there may still be a non-functionality, but it's outside this particular function. So you call it with the same argument a, and you supply the time. So this is a function, and this is not. What you can do with b now is that anybody can run that thing at any time and not worry about getting the right answer, because nothing is going to interfere. There's no way for another program to interfere with it. This means that we can get parallelism also out of f. So as the loop produces a instances of f, they can all run in parallel because f is considered, f is a function. So the composition of functions is another function. That's the essence of functional programming, is this. Every time you run it with the same input, you get the same output. Did I skip something? No. Okay, here's a more complicated form of a functional program. And it's going to perform generate, map, and reduce. So it's going to, and this is here laid out as it might be executed on a machine. There is a function f that is being run, in this case k times, and then all of the results get added together and the result is produced. So how does it work? Well, it's a recursive function the way it happens to be written here, and it works by splitting the input as long as the input is known. You have a method of deciding that it's efficient to split the input. The efficiency is going to depend upon how complicated is f. If that function is really simple, you don't want to split it too many times because then you're going to be spreading the load out, and the overhead of spreading the functional computation over a lot of different cores isn't going to buy you very much. So at some point, this guy answers and says, it's not efficient with this particular input function f to split this and to spread the load any further. So at some point it was decided when the list became K long that all of these are going to be run on the same machine. And that's what this guy down here is doing. So his answers all this work gets computed on one particular core. But that gets repeated some number of times, A over K times. Then the summing takes place. Now I've done this split on this particular diagram just by splitting it too, but you can imagine being split many more times all at the same time to again, increase the efficiency and reduce the number of iterations that are done in the recursion. The point being that this is a simple example of how computations, when you have functions, you can spread them out over the machine because you know that the functions are not going to interfere with one another. And all of these components are functions. So that's the kind of thing that we want to do in this machine. We also want to be able to start and stop and move and copy and so forth functions and run them at any time because things may fail. You may send a computation off to some core and not get a response back. If you don't have a function, the danger in rerunning something is that you don't know what it's done. It's possible that if it had shared memory in it and you started that function up, it didn't complete, but maybe or maybe not did it modify some memory that somebody else is going to be looking at. Did it get that far in the execution? Again, with functional programming, that's the sort of thing you don't have to worry about because it didn't. You can just repeat the computation. So we want to be able to restart, move, copy, so that we can do these kinds of things, and reliability or robustness that Bob also talked about is a part of what this language is going to try and support. So in order to have these capabilities and not have to do heavy analysis, deep analyses of individual programs, we just say, everybody write your programs functionally. And so the domain-specific language that I would like to put together is going to be a functional language. Now the problem with that, and functional languages have been studied for quite some time, but again with Multicore we think we're going to have much greater efficiency and be able to actually make them real, is that is somewhat incompatible with the idea of state. And real systems do have state. So we have functions that are running, but we have state over here. Functions are going to modify state, or they're going to cause state to be modified by some means, which we have to work out. Now, a state that we're talking about is like a variable in the application domain, and here's just a couple of examples of what a state would be. These are the kinds of things that when a function is run, and say it's an estimator, it's going to change what the spacecraft attitude is. It's going to change the state vector of the filter that's running. Or when the telemetry is running, the amount of stuff that's in the downlink buffer is going to change. So those are the kinds of things that we have to keep track of. Those are the states. But again, we have functions which do not have state and don't work with state. In particular, as examples here, it don't mean a general concept of state. So we're talking about at the particular application layer that we're working in, it's the state that we need to keep track of and somehow put together the notion of a functional language with this state. So as a first guess as to what this functional language would look like, we really want to specify exactly what the state is in the system, because it's hard when you look at an arbitrary C program. It's very difficult to determine which variables are state and which are not, because state is not something that is a part of the concept of C. So we add or incorporate the state keyword in the language, and we're saying here that this vector is state. and it's inside a module because we want to have distributed computation. So you can look at it as a very object-oriented kind of a language. And we have the parameter keywords, because parameters are, at least at JPL, the way we define parameters is they're a special case of state. They are state that can only be changed by action on the ground. We also define an interface, which in this particular example there's only two of them. There's an initialization, and the one we'll use as an example is this GNC function that's called at a 64 hertz rate and has a single argument in it. These guys, this guy in particular, is written to be a function. So how do we get this vector, for example, to be updated every time this function runs? Oh, and there's a couple of restrictions. You don't write static anywhere in your program if you're a C programmer. There's no pointers to state, and there's no pointers within state. Now, pointer here means hard memory addresses, because we want to move things around in particular. And so if you want to have pointers, you can substitute arrays, and just the pointer becomes the index into the array. That's the pointer that you have. So in the end, there's no other way to define state. So let's take a look at a little example here. Again, this is the declaration of this particular module. And on the inside of the function, we're going to say that this guy is using the state vector called GNC vector. One could look at this as, the way we're going to do this is an argument from the user, the application programmer, and this is going to be the list of arguments, where there are more than one, that the system is going to supply. The system is the guy who's got the state and he's got the function. Let me go graphically. Ooh, where's my picture? Oh, there. The system is going to do a lot of work for us. It's going to keep track of the state, and it's going to supply the state to the function. It knows it's going to do that because we said so right here. Now, another thing about the language that we need to do is to make sure that even though this program is going to compute new state, it's going to say this is our next state, the next time this function is called. We're going to separate those two parts. So x refers to the current value of x, and next refers to what it's going to be the next time the function is called, in the future. And there's a rule. You cannot put this guy on the left-hand side of an assignment, and you cannot put this guy on the right-hand side of an assignment. So we've separated state from function, and we have separated the current state from the next state. What that's going to mean then is that whenever this function runs and we start executing in here, the current state is never going to change. We know the input variables are not going to change, they're passed by value. So all of the computations that take place in here, written in a functional language, we're going to still have the function. This is still going to remain a function. When it completes its running, I'll go back to my picture here. When it completes its running, the result that comes out for the new state goes back into our storage that's detached from the function. So we've separated state from function. We have these two worlds. The idea being here, again, that we have functions. The inputs, one of them being the application argument, and the other one being the state, all of the state that that function asked to look at. None of it's being modified in here. The results come out, and if this is the new state, that goes back into the state after the function has finished its execution. This is certainly not current practice. The way we do things now is that we have variables in C, and we write programs. And if, say it's a program that's maybe 1,000 lines long, just to pick on something very large. At line 100 in that program, it's quite possible that somebody's going to say, okay, change this state variable and set it to 5. Go a little bit further in the program, and maybe at line 200, change state variable x of 3 and set it to the result of this computation. The result of that is that as you run through the program, you have to keep track in your head, and anybody who reads the code, what's been changed at what point in the program. It can be difficult to, it's a source of errors. And in fact, the GNC team on MSL, the guys who write the estimators and controllers, decided in fact that they'd had enough errors in the past, enough trouble in the past, that they wanted to separate current state from next state. So in fact, that code is written without the aid of a language, and therefore without the aid of detecting whether or not they made a mistake and forgot or took a shortcut someplace. The attempt was in fact to write the EDL code, the EDL code for MSL in this functional manner, so that instead of modifying the state as the function ran, it actually kept two copies. There is the current state and there's the next state. And at the end of the processing and computing what the next state is going to be, they copied the next state into the current state for the next round. And the reason that they did that was simply because they wanted to avoid mistakes in the past when people lose track of whether you have modified a variable or not. So what I'm trying to kind of point out here is that there's not only good computer reasons for separating current state and next state and keeping state separate from function, but there's also just a good practical reason, and that is of making the programs easier to read and write, and they felt also a lower chance of making a mistake. So the idea here is that the proper practice is you keep those distinct, and again, emphasize the current state does not change during the execution of the function. So I also like just a little further mathematical argument here, but if you think back to your, well, maybe you work with partial differential equations and machine solving of those, or estimation or finite state machines, a lot of the equations look kind of like this, just to pick a form, where the current state at time t and some input, there's a function f that computes what the next state is going to be, and a function that computes maybe some output. So this is analogous to our function that we had of the 64 hertz GNC. We've sort of combined f and g, and it's possible that the language may change and actually separate those out, but for the moment, they're combined. But you'll notice that there's a separation here, and because mathematics doesn't know anything about memory cells, the changing state is represented as a sequence of states. Now, we could, of course, in the computer do the same thing. We could have loops and recursions that in fact keep track of all of the computations, but that's probably a waste of storage, let's put it that way. So we cut it off and we do an actual replacement after the function is executed, but it's out of the reach of the programmer. The programmer has no control over that. He just computes what the next state is going to be, and when the function's done, it does the replacement. So it looks to some extent like this, but certainly the function behaves in a functional way. Again, the reason it's a function and why we want it that way is so we can move it, we can restart it, we can recompute it, and as long as the arguments are the same, we'll always get the same answer. So, some examples of how this can help in computing and making a system robust is an example in Graceful Degradation, where, for example, you have image processing going on, and you spread the picture out, the image that you're going to analyze, over a whole bunch of separate cores. Now, if you chop the image up into the pieces, then of course each piece can be done individually. Usually there's some consideration of boundaries and so forth, but there is individual computations going on, and they each report their result to another function in the system. And it's the job of that system to collect all of those results together and to feed those off to, maybe it's an estimator who's going to be using the results of the image processing. So if you have functions in here and one of them dies, for example, a core here in red has died, the absence of that in this particular example isn't going to impact the result. So you can just continue on running. And in fact, maybe more pictures are continually being processed, but the system, maybe it takes a little while to recognize that that core has in fact failed and is not reporting results. But the computation will continue on. It's just that the result may be a little bit less accurate because you're not getting the response from all of the cores that are there. And then you can pick a core anywhere in the system and have it run in place of the one that broke and get back your precision that you wanted to have. So that's a very simple example, and we know that we can do this because each of the guys who's running here is a function and doesn't leave any shared memory traces behind. And we can continue on even in the face of errors and even in the face of not finishing the computation. Now, a slightly more complicated example in this system is when we're interested in robustness, and one way of achieving that is to use redundancy. And of course, one of the most well-known techniques of that is triple modular redundancy, where you take 3 computations and you vote them, and at least 2 need to agree in order to come up with a result. So in this particular case, what we've done is we've said, well, we have a computation. And in fact, we're doing this in one of the R&D projects that we have. We decided that the filter itself, there's an image analysis part, all the results go into a filter. And we said, well, the image analysis part has a little bit of graceful degradation associated with it. But the filter is a single fault tolerant, what's the term? It can't fail. Otherwise, we don't get anything. So if we want to increase the reliability of that, we can triple modularly, redundantly, run the filter. We feed the same inputs that we would normally feed to one filter. We feed them to all 3. And then the results come out and they get voted. And we know that we can do that because the filter is a function. If you write in a functional language and you're guaranteed that every time you write a filter, it's a functional one, you don't have to think about this happening. It can happen underneath you without you having to worry about it. The work has already been done for you, in a sense. System code that knows what it means to create a triple modular, a TMR form out of a particular function can do that for any function. And the system can decide, this is the function that we want to replicate, and this is the function we want to vote. So if we happen to have an error, and this is the guy who is not producing the same answer as the other 2, we're still running because these 2 guys agree and the voter has passed the result on. But what we want to do is to recover and reinstitute the triple modular redundancy. So we can do that by grabbing another core, and since it's a function, just like its other 2 copies were, we don't have to worry about when we do that. We just have to make sure that the inputs that go to each of these guys are the same, and their outputs are guaranteed to be the same, unless there's an error. So the triple modular redundancy can vote not only the answer, but also what is the updated state, because that is also available as a separate entity. Then another, what this is headed towards is the following idea, that if we look at all of the computations that are going on at the bottom as being the leaves of a tree. This is where all of the work that we think about normally that's taking place on a spacecraft. But we have a hierarchy of supervisors. And it's the supervisor's job to oversee the function that this guy does, that at any particular time is implemented by some one or more threads. So he has some understanding of what this thing down here is trying to do. And if he, for example, sees that there's an issue or sees a problem, he can replace this filter with perhaps another one that has different behavior, doesn't use the same style, and maybe there's a chance that it'll work better. This is kind of an idea that's, shouldn't say kind of, it is the basis of the Erlang system that some of you may be familiar with. And what we did was to say, well, we'll do that, but we also want to do one other thing. Since this guy is responsible for, let's say in this case, the filter aspect of this whole system, and over here perhaps we have the image processing part, and this guy is responsible for that. So maybe the camera plus the analysis part, and this guy would be, say, the filter plus an IMU or other sensor. We attach to that a supervisor over them, and of course the tree can go up. But the idea being now is that we're working on this within this sea of cores that we have on board the spacecraft. And remember, power is reliability times speed. We may get or suggest or tell the supervisor at the top level, this event called EDL is coming up and we want to increase the reliability. We're going to up the power, we're going to make more cores available to you, increase your reliability. That information goes down to the lower level supervisors who know how to increase the reliability of what they are doing. On the image processing side, he may decide, for example, I don't have to do anything, I'm already reliable. I can handle failures. But on the filter side, it may mean that what he has decided to do in his bag of tricks, in our particular example here, is he says, I want to institute PMR. That's how I'm going to increase the reliability of the filter. So he replaces this one thread with these 3 to 5 threads that are going to do this work. And he does that in real time. So the swap takes place. First step is to create these threads, including the voter and the fork, and then to wire them up. And the last step then is to take this path and move it to here, and that path, the end of the arrow gets put on that guy, and you're ready to go. So that swapping over can happen in real time very quickly. And the reason we can do that, again, is because we're working with functions. I want to emphasize that this kind of thing, this doesn't have to be a filter. It can be anything, any function on the whole system. And it's this guy who decides how that's going to be done. So what I wanted to get at this point across is that we have a principle, and that is program everything with functions and separate functions from state. And if you do that, the claim is that not only will your programs be written more reliably, but some other things are going to fall out as well. One of them is this, the idea of what I would call automatic telemetry. You may not want to build a system that has telemetry where engineers sit at a console. You may want to go beyond that. But if you wanted to build one, we have, at JPL, the way we do it is that we have two kinds. There's EVR and EHA. EVR means event report. So if something happens during the execution, it may be nothing more complicated than I change state from cruise phase 1 to cruise phase 2. And then a message goes down to the ground. And the ground feels good because they see that it was supposed to happen at that time, and indeed it did. The other is what we call engineering housekeeping and accountability. How that came up, I don't know. But what that is doing is downlinking state variables in our system. Now in MSL, it's memory cells in C, some of which may be state, some of which may be intermediate values and so forth. But these are kind of two different kinds. This is transmitting state, and this is transmitting events. So the idea behind the construction of telemetry and the way what I'm pointing out as far as the automatic is concerned is that on MSL, we spent thousands of hours writing code that would output these things and output these things, and testing them and making sure that they were all coordinated and that the correct values came down. It was an extraordinarily expensive undertaking. And at every mission, the number of channels and the number of events that get reported keeps going up. Now there's in fact, two different streams of these things. Some of them are history records, and they go into solid state memory, solid state recorder, and they non-volatile is the word I'm looking for, non-volatile memory, and they stay there so that if we're successful, we can replay back to the ground everything that happened and get a lot of engineering information about what the ride down to the surface was like. And it's a subset of that stuff that goes to the consoles in real time. But again, we spent a lot of time getting this stuff, testing it, making it right. And so my claim is that one of the fallouts from having what I would call a principled approach to writing flight software and writing functions and keeping state separate from function is that other things fall out of that. And I would claim that automatic telemetry is one of those, where all the programmer has to do is that in his definition of a module, next to where the state variables are declared, is to put a little keyword that says EHA or EVR, and that's all he does. Because by construction, the translator that's going to take that domain-specific language and turn it into something else, probably C, that all of the work that people do is now relegated to simply building the translator correctly. And again, I would say that the reason that I believe that you can do this is because of that separation of function from state and knowing that the system is taking care of keeping track of the state for you. So an interesting thing actually about the event reporting is that what we're noticing here is that a state change is an event. So whenever we replace the old state with the new state, or the system does, it can check to see what has changed. And if it has, send an event if that was so marked by the programmer as being an interesting event that somebody wants to know about. Then the question is, should it be the other way around also? So state change implies an event, but is every event a state change? So with some encouragement from Mitch Ingham, I decided to try this. And I think that I'm going to institute this as an axiom that says that the only way that you get an event report is if there is a state change. So you think a little bit about what kinds of events there might be that are not represented directly by state. For example, you may be controlling something that's getting close to a boundary of control authority or acceptable position. And you may want to know about that. And so you may have an event in your program that we got too close, here's a report, somebody ought to do something about this in the future, or do something, send something up to the spacecraft to change what we're doing so that we don't run into issues. Now you can also imagine a lot of this stuff being done automatically, but for right now, we would be doing that by hand with controller intervention. If there is an event like that that's important enough, the thinking may be, well, maybe we ought to trend that and find out what it is, what it looks like over time. So we can see if we have a fundamental control problem or there was an error in data or something like that that took place and it was just a momentary blip. But if you're going to trend something, you're going to have to keep track of it, which means you have state. So immediately, if it's an interesting event, it sounds like, more likely than not, there might be some exceptions, but I'm going to bet that it's worth keeping track of, and therefore the event will be reported because there was a state change. One of the things we'd also like to see in this spacecraft that has lots of processors in it is that we would really not like to have to reboot the system. So why do we reboot? Well, in MSL, for example, there's a couple of reasons for why we reboot. One of them is that's how we get new programs up to the spacecraft. That's a solvable problem by having dynamic loading of new programs. It's been done in many different places. We just don't happen to do it. Another reason for doing a reboot is that, for example, for EDL, which MSL did do a reboot, I don't know, a few days ago, cold boot of everything. Why would they do that? There was no reason to, except nobody knows what all the state is in the spacecraft. And the theory is that, well, every time we tested EDL, we rebooted the test system and the flight computer that was a part of that test. Just in case there's something going on that we don't know anything about, because we don't know all the state in the system, let's do a reboot and hope that if there was a problem, there was something that was wrong, maybe the reboot will cure it. So that's kind of a philosophy that's based on sort of negative rather than a positive idea of, well, why don't we know all the state? And why don't we have either checking by system engineers by something as primitive as spreadsheets that say, well, what is the state supposed to be before we commit to this event? Or, again, those could be constraints that are running in another program whose job is to make sure that the spacecraft is in the right state before this particular event arrives. So one of the other things that this separation of state from function has given us is that we now have a chance of having a complete inventory of all application state in the system. It can be hard to get operating system state because the people who wrote the operating system probably weren't quite so obvious about what is state and what is not. And then there's hardware. We also reset the computer, and a lot of its stuff gets cleared out. So it is not a 100% solution, but we do have all the state inventory for the application code. And in fact, for any hardware that we build, we can make it so that it too satisfies the requirement that there is a state inventory, because hardware is written these days by writing programs, and it gets compiled into hardware rather than getting compiled into code. So just as we had rules that said you can only create state in this way, therefore the translator can produce the inventory for all the application software, we could do the same thing for all the hardware that JPL builds. That doesn't cover everything else, but maybe the idea would catch on and we could have state for absolutely everything. Again, the reason that we are able to do this is because we have separated state from function and we only created state in one particular way. Now, it is also possible, and this is sort of a completeness idea, that it's possible for the programmer to declare a state variable that in fact is never used as a state variable. And that can be detected through static analysis. And this is a little function that one can write, and since we have a translator, we can build that in to the translation process and decide whether or not any one of those given state variables, given in the sense that the programmer said it was a state variable, whether it actually is a state variable. And if it's not, we tell them, you know, you made a mistake, it's not a state variable. It may be a warning, it may be an error. So the bottom line here is that in the system, we have a functional semantics. Two functions are concurrent unless the output of one is the input to the other. That allows us to spread the computations out. They also don't interfere with one another because they are functions. And that is to be contrasted with the sequential semantics of von Neumann or C like language, where it's really the opposite. Two functions are sequential unless you can prove that they're concurrent. And that usually takes an analysis that may be incomplete because you don't have a lot of information about the runtime. You only do it statically. And that's one of the reasons for why a functional language is a useful thing. So, in summary, what we have done here is to note that the hardware really drives what we can do, and that we're going to see eventually what I call a sea of cores on the spacecraft connected by high-speed links. And that what we want is this kind of a behavior to be dialed in, that a sort of a policy-driven type approach, implemented in such a fashion that the programmer, the application programmer, doesn't have to think about it. All the hard stuff is in the translator and in the system code that's going to see to it. We said that that's a functional language is the best approach that I could think of for accomplishing that. And then we recognize that state in a functional language or in a functional setting really requires that we keep those two worlds separate, that we don't mix them. So we separate them. I guess I forgot to mention that copying of the next state into the current state when the program has finished is an atomic operation. So it follows a theory again in the sense that you instantaneously, as far as the programmer is concerned, since it happens behind where he can see, it looks to him and to everybody else as if that function, as if that module had changed state instantaneously. We can know the entire state, which moves us towards the idea of having no reboots, a continually running system. And another fallout was automated telemetry. Again, all of this coming from a recognition of a fundamental principle of functional languages and keeping states separate. And I think somewhat in vein with what Bob was talking about, these things that fall out are a natural consequence of that particular decision. And you gain a lot of advantage by sticking to a theory that's good and implementing the system based on that. So that's it.